screen, right?
Now presentation mode, and please start.
Am I on?
Yes, yes, yes.
Presentation
I can
mode.
see.
You can take the presentation mode.
Presentation mode.
Presentation mode. Okay, that means this is screen, full screen mode, right?
Yes, now it is on.
Okay.
Please start.
So let me quickly go through the slides, because if I start talking extempore, then I will go outside the time limit which is set there. Now I think I have only 35 minutes according to the clock in front of me. So in 1927, the double Nobel laureate Eugene Paul Wigner was the first person to apply group theory to atomic spectroscopy through rotation matrices. There is a theorem which is considered as one of the cornerstones in the whole of mathematical sciences, which is called the Wigner-Eckart theorem, which separates the physical and geometric aspects of the matrix element of a tensor operator. Now, the reason why I'm talking to you physics is mainly because it is through physics and through angular momentum that I entered into hypergeometric functions. And you will see the intimate connection which I have been able to establish. By 1928, Hermann Weyl wrote the first book on group theory and quantum mechanics. It was followed by Wigner's book in 1931, van der Waarden's in 1932, Avron Venkatarayudu's in 1953, and Gelfand, Minlows, and Shapiro in 1958, Martin Hammermesh in 1962. So when I joined research in 1962, the latest book was Martin Hammermesh. Today, of course, you have an enormous amount of literature which is available for you on group theory. There are encyclopedias which are available. So I will not go beyond this to tell you about what is available today. Now, the theory of complex spectra, that means both atomic, molecular, and nuclear spectra. These were the things which were being done at that time in the experimental labs. And people wanted to find out how to account for these experimental data. What is the theory which you have to provide? Once they realized that the classical mechanics has its limitations, that you cannot account for atomic, molecular, and nuclear physics in the framework of the classical physics and Newton, quantum mechanics developed. So that it takes you to the physics part of it. Now, to me, for the part which I want to pinpoint, which is a small, what shall I say, grain in the whole area of complex spectra, the work which was done by a person called Giulio Raka, an Israeli mathematical physicist, he wrote 4 papers in the years 1942, 43, and 49, which are considered as the most path-breaking papers where all the mathematical tools which are necessary were developed. Today, the name has been given as quantum theory of angular momentum. And the entire quantum theory of angular momentum, QTAM as I call it, was developed by Julian Schwinger in the year 1952 from an entirely different standpoint, which is known as the second quantization framework. And all this has been reprinted, whatever has happened before in the 1960s and before that. That is from the moment quantum theory came into existence and angular momentum had its starting point till 1965. The best reprints have been put in together by Larry Biedenhahn and another gentleman by name Van Dam. And that is probably the source material which I can make it available for you. Make you refer to if you are interested in. There were 2 short notes which are hardly 2 pages long, which were written by a mathematical physicist of great reputation. There is a phenomenology which is known as Regge phenomenology in particle physics. This gentleman is by name Tullio Regge. He wrote 2 short notes on the symmetric groups of 3J and 6J, what are known as 3J and 6J coefficients, in an Italian journal called Il Novecento. And these 2 short notes triggered my imagination. In 1963, Larry Biedenhahn, another giant in the area of quantum theory of angular momentum, coined the terminology and called this as a calculus which is completely different from the normal calculus, which is Newtonian calculus. This is known as the Raka-Wigner calculus. So it is to Raka-Wigner calculus which I'm going to refer to. And to me, in my opinion, the best paper which I came across was around 1972 by academicians Oredinsky and his collaborator Shalepin, in a journal which is called Soviet Physics Journal, Uzbeki, and it is entitled Klebs-Gordon Coefficients Viewed from Different Sides. In my opinion, this is perhaps the most important paper that has been written in that particular area, and it gives you a connection between what is called angular momentum, quantum theory of angular momentum, and various branches of mathematics. Name the branch of mathematics, they have shown the connection which exists with that branch. The two volumes out of the Encyclopedia of Mathematics and its applications were devoted to angular momentum in quantum physics. Volume number 8 is angular momentum in quantum physics, and volume 9 is Raka-Wigner algebra in quantum theory. Both these appeared in the year 1981. And I'm glad to tell you that in an appendix to Raka-Wigner algebra and quantum theory in 1981, a whole section of that appendix is based on research work which I had done, which was establishing the connection, beginning of the connection between quantum theory of angular momentum and hypergeometric functions. I wrote a monograph in 1993 when I had sufficient enough material to put it down in the form of a book. So this is a research monograph published by Springer Verlag along with Naroza for Indian distribution, Springer Verlag for the world distribution. This was written by me with my student by name Rajeshwari, and it's a research monograph which pertains to angular momentum, what is known as coupling and recoupling coefficients, and their relation to generalized hypergeometric functions of unit argument, their Q generalizations, what are known as basic hypergeometric series and so on, their Q generalizations, and their relation to orthogonal polynomials and numerical computational methods for computing these angular momentum coefficients. In those days, I mean, today also, people do not refer to these coefficients, but in those days, programs were not available and people had to do numerical analysis to compare theory with experimental data. So that is why I had to learn something about these angular momentum coefficients. And this angular momentum, as I told you, is the one which provides you the quintessential mathematical background which is necessary for you to understand the spectra of which occur in atomic, nuclear, and molecular atomic spectra, molecular spectra, nuclear spectra, that is the energy levels and things like this, that's called as spectrum. So those spectra had to be understood, those values had to be reproduced, and that would give us an understanding of the physics, which is the mathematics, which is required to understand the physics of the problem, which is made available to you by the experimentalist. So the connection between some of the selected topics in which I got interested were the connection between what are known as 3J and 6J coefficients. I will explain to you briefly what these are. Rather than go into the depth, I thought I would like to make the fundamentals clear in the initial stages so that you will get an idea of what is it that I have done. So the connection between, so what are called as 3J and 6J coefficients and generalized hypergeometric function has been established. Complete connection has been established. The transformation theory of generalized hypergeometric functions related to various forms of hypergeometric functions. These were named after the discoverers of those forms. One of them is known as the van der Waals form, another is known as the Wigner form, another is known as the Raka form, and another is known as the Majumdar form for one of those coupling coefficients, which is known as the 3J coefficient. Why 3J? You will understand from the next slide. So angular momentum coefficients have connection, intimate connection to orthogonal polynomials. And one could talk about polynomial zeros of angular momentum coefficients. This was one area in which I was able to make a lasting impression, because that is where I was able to establish a connection between hypergeometric functions and multiplicative Diophantine equations, and gave a complete solution to the problem of what are known as non-trivial zeros of angular momentum coefficients. There is a particular scheme for evaluation of a polynomial, which I do not know how many of you are aware, which is known as the Horner scheme for polynomial evaluation. And this polynomial evaluation, if you take 1 plus, I'll give you a simple example orally. Supposing I want to calculate 1 plus x squared plus x cubed plus x power 4. Just the simplest polynomial in one variable. Now, if I were to calculate it up to x power n, let us say, you will find that when you take x power n, n minus 1, every multiplication, x squared requires one multiplication, x cubed requires two multiplications. So the operation of multiplication takes a lot of time on the computer. So if you look at the n-dimensional polynomial, polynomial of degree n, let us say, as I said, 1 plus x squared plus up to x to the power of n, you will find that the number of additions is n, because 1 to x plus n, x power n, 1 plus x squared plus x power n, there are n additions which are there. But if you take the multiplications, x squared requires one multiplication, x cubed requires two multiplications, and x power n requires n minus 1 multiplications. So it will require order of, when n is very large, if the polynomial is of large degree, then you will find that the number of multiplications will be of the order of n squared rather than n. And when n is large, n squared will be much larger. And therefore, the time taken for computing was very large. The Horner scheme for polynomial evaluation does something which eliminates the powers of n in a very simple manner. I'll give you the example of a polynomial of a finite degree, let us say 4 or 5. What Horner scheme tells you is take 1 plus x, bracket it, multiply it by x, add 1, bracket it, multiply it by x, add 1, bracket it, multiply by x, add 1, until you have x occurring n times in that folded scheme. This is a folded multiplication scheme, which is for all polynomials. And therefore, a polynomial requires, in this case, because you have written it in a folded form, you would require only n multiplications and not n squared multiplications. This realization made me look at angular momentum coefficients, for which I was able to establish a connection between angular momentum coefficients and hypergeometric functions. And I came across sets of hypergeometric functions, not one, but sets of hypergeometric functions. And I had to evaluate these hypergeometric functions, making use of the Horner scheme. And this was an industry out of which I was able to produce a couple of PhD students, write a research monograph, and publish quite a few papers. Now, in the process of my researches, I have come across several interesting things. And since you people are interested in hypergeometric functions, I would like to tell you that a hypergeometric function has a three-term recurrence relation. All of you know orthogonal polynomials satisfy three-term recurrence relations. There is an intimate connection between hypergeometric functions and orthogonal polynomials. And therefore, hypergeometric functions also satisfy three-term recurrence relations. Now, it was my pleasure to discover four-term recurrence relations, and which I think are extremely new in the area of hypergeometric functions. Now, these new results are the ones which I have shown here, where you can see that I will have, you can have three-term recurrence relation, four-term recurrence relations, and you can write it down for a general hypergeometric function. There will be a multiple term recurrence relation. So these recurrence relations are the ones which I consider as new results in hypergeometric series in recent times. They were published hardly about a few years ago. For those of you who are interested, you can write to me. I will send you copies of the papers which I have written on this. Now let me go into the main crux of the problem. What is angular momentum? All of you know that we are standing or sitting or wherever you are on Earth, that Earth is spinning at a speed of 1,500 kilometers per hour. Now it's a simple calculation for me to tell you, take 2 pi r, the circumference of the Earth. You take 24 hours from sunrise to sunrise. So take 2 pi r divided by 24, you will get 1,500 kilometers per hour as the speed of the Earth. The place where you are sitting, the place where I am sitting, it looks as though it's absolutely stationary. But believe me, if you have not realized this, and if you have not told this to your children, please go home and tell them that you are sitting on a spinning top, which is spinning at 1,500 kilometers per hour, and you don't feel it. Isn't it remarkable? Have you realized it? For those who have not realized it, this itself is something which is worthwhile remembering me in this context. So angular momentum is when a particle, the sun is at the focus of an ellipse, and the earth is making an elliptic orbit about this. So all of you know this as a simple fact. So the earth is going around in an orbit. So it is called orbital angular momentum. The earth is moving with a velocity v. It has a mass m. Therefore, it has a linear momentum p, which is m times the velocity, 5.1, which you see there. Then, if it is with respect to an origin, and r is the position vector, because for the earth also, you have to have some coordinate system wherever you are. You have to choose a coordinate system which has to start from a given point. So from the coordinate point, from where you are going to measure from the earth, if something is going to, a spacecraft is going to be sent, a space mission is going to start, the position of the spacecraft from the earth, from the center of the earth, or whatever is the reference point, that is r, let us say. And p is its momentum. Mass times velocity is called momentum. And the vector product of r and p, which is called r cross p, is called orbital angular momentum. And the whole of quantum mechanics enters in a very simple manner when you realize that Eisenberg in 1932 discovered the fact that position and momentum at atomic, nuclear, and molecular levels are not things which you can measure to the same degree of accuracy. There is an uncertainty. If you know the position exactly, then you do not know the momentum exactly. These are known as canonically conjugate variables. That becomes physics. So I will not go into that detail. But the whole of quantum mechanics started with an ad hoc replacement of saying, let the momentum be replaced by minus IH cross del. And del is your del operator, and that's how your mathematics comes into the picture. And then you can write down the equation which is satisfied by angular momentum, and that becomes a second order ordinary differential equation. And the solutions will be in terms of, if L is the orbital angular momentum, r cross p is what I called as orbital angular momentum 5.2. Therefore, it has got components Lx, Ly, and Lz, which can be written because of the operator replacement suggested by in quantum mechanics. You replace p by minus IH cross del, and that tells you that Lx, Ly, Lz are now operators. And if you now take the fact that position and momentum, 5.11 tells you that position and momentum do not commute, and there is a there is a commutation relation between them. If they commute, then xkpl must be equal to 0. If xkpl do not commute, that means their difference, xkpl minus plxk, that is what is meant by a commutation relation, that is not equal to 0 means they are not commuting variables. So these are known as canonically conjugate variables, and there are pairs of such canonically conjugate variables. The delta KL, which is written there, is the Kronecker delta function, which all of you know. So one has to calculate now, instead of for position and momentum, 5.11 tells you there is a commutation relation, which is the Heisenberg uncertainty principle in algebraic form. Now, angular momentum, Lx, Ly, Lz, if you look at Lx, it is ypz minus zpy. Supposing I take a commutation relation between Lx and Ly, then you will find that I have to take a commutation relation of ypz minus zpy with zpx minus xpz. So Lx comma Ly is this product. So 5.17 tells you, 5.17 tells you how to calculate such matrix elements and how to make use of the uncertainty principle, which is related, which is given as xkpl equal to ik delta L. And eventually what you will get will be, out of this, a commutation relation that Lx and Ly will give you Lez. Ly and Lez will give you Lx. Lez and Lx commutation will give you Ly. or if you put them all together, making use of the tensor notation of what is known as a Levi-Civita symbol, LKLL, commutation duration 5.21, LKLL is I epsilon KLM LM for all KLM 1, 2, 3, because we are in three-dimensional world. So LX, LY, LZ are L1, L2, L3 are the three components. Now the operator, which is the length of the angular momentum of vector. Angular momentum is a vector. Therefore, the length of this vector is L squared, which is Lx squared plus Ly squared plus Lz squared. Now, if you look at the commutation relation of L squared with Lx or L squared with Ly or L squared with Lz, you will find that they commute. So that is known as a commutation relation, which is satisfied by, wait a second. So Lx, Ly is going to, L squared is called a Casimir operator. Yes, an operator which commutes with all the generators of the group. So L squared and one component, Lk, is equal to 0. One component you take it. If you take another component, then you will find that Lx, L squared will commute with Lx, L squared will commute with Ly, but Lx and Ly do not commute. That's what we started with by saying that Lx, Ly commutation relation is not equal to 0. Therefore, you will find L squared will commute with all the Lx, Ly, Lx or Ly or Lz. So L squared is called a Casimir operator. These are simple facts which can be worked out in detail if you are interested, and L squared is called the Casimir operator. Now, L squared and one of the components can be used for labeling a state. You have to describe, in quantum mechanics, you have to describe every particle is in some state. So the state will be described by means of a vector like this. YLM are functions which you know, you are all people in special functions. YLMs are spherical harmonics. These are solutions of the second order ordinary differential equation in spherical polar coordinates. If you write down the Laplacian, write it in spherical polar coordinates, then you will find automatically YLM functions come in for the angular part, the theta and phi part. So those are the ones which are required for your angular momentum here. So the YLM functions become important as the eigenfunctions of angular momentum. Now, orbital angular momentum, the Earth is going around in an orbit, therefore it has orbital angular momentum. But I started by telling you that the Earth is spinning around about its own axis. That is what is called the spin of the Earth. And it was the genius of Wolfgang Pauli who introduced that concept, which is available at the macroscopic level. You feel it every day. You are sitting on the Earth. The Earth is having both orbital angular momentum and spin angular momentum. Spin angular momentum is what makes it go around about its axis. Day and night is possible only because of spin of the Earth about its own axis. So these have been incorporated in the atomic level, and that becomes the place where the whole of quantum theory of angular momentum developed, and you have to get the algebra to work, and that algebra requires various tools. So the tools are like this. I mentioned to you that L squared and one of the components commute. Now, if you take S squared, which has a spin, is also like orbital angular momentum, but spin is about its own axis. It satisfies the same commutation relations, is how we escape by saying that. And L and S satisfy the same type of commutation relations. So the total number, when you have a particle which is going around an orbit and going about its own axis, it has two angular momenta. It has orbital angular momentum and it has spin angular momentum. Then you ask the question, okay, if there are two angular momenta, what is the total angular momentum? That's how the concept of addition of vectors comes. And J, the total angular momentum, 5.1.113 tells you J is equal to L plus S, which means the orbital angular momentum and the spin angular momentum can be combined to give you a total angular momentum J. Now, if you have a coupled system, that is, you have two particles, one or either two particles J1 and J2, or a particle which has got orbital angular momentum and spin angular momentum. If you have two angular momenta, L and S, or J1 and J2 as we call it, and their sum is J, or their sum here is J is L plus S, then what are the total number of generators operators which will commute among themselves. I mentioned to you that L squared commutes with only one of the components, not all the three components. It commutes only with one, because if you take one more, those two will have a commutation relation which is not equal to 0. Therefore, these are known as the name which was coined for this is complete set of commuting generators. This has been coined by Eugene Paul Wigner. So for a given angular momentum, you will get J square L or S or J, as the case may be, angular momentum. So the square of the angular momentum and the z component of the angular momentum are the ones for which you have to choose labels. So the mathematics enters in the following way, that if you have an uncoupled system, you have, let us say, J1, M1, J2, M2, that is the angular momentum and its projection. The coupling of them together will give you J1 and J2 will couple to give you J. So J1 and J2 will couple to J, means M1 and M2 will add to give you capital M. So one of them is a vector addition, another is a scalar addition. M is a projection quantum number, and therefore this is like YLM. L is a vector quantity, M is a scalar quantity, right? So YLM functions are typical of angular momentum eigenfunctions. So the total number of the state of two particles, the two particles can be either in a coupled state or in an uncoupled state. That is what happens when you are looking at an atom with an electron going around in an orbit. The electron is going in an orbit, therefore it has orbital angular momentum. It is spinning about its own axis, therefore it has spin angular momentum. Therefore it has a total angular momentum of J. That is how angular momentum enters in for a single electron. And believe me, atomic physics, molecular physics, and nuclear physics does not deal with only one atom, sir. It deals with many particles. Therefore, one has to develop the theory of how do you add two angular momenta. 5.1.12, 5.112 tells you J1 plus J2 is equal to J3. Now, you could have three angular momenta, in which case it will be J1 plus J2 plus J3 will be equal to capital J, and so on. Now, it is sufficient for you to look at the interaction. There is again a little bit of physics which goes in. The interaction is only a two-body interaction. Two-body interaction for common man and woman. That's a two-body interaction, right? That's how life goes on. So in the same way, if you look at a two-particle interaction, like in a hydrogen atom, there is a proton, there is an electron. Or take a neutron, which is a nucleus, it has got one proton and one nucleon. So a two-particle system like that, you have to talk about its total angular momentum. So the point which I wanted to drive home is given in equation 5.121, which is there, which tells you that angular momentum L, orbital angular momentum L, and its projection mu is written in a particular notation. This is known as the Ket notation. The beautiful way in which the concept was introduced by Dirac. You write the word bracket, B-R-A-C-K-E-T. Now you put one left bracket before bra and one right bracket after ket. And you now look at BRA, draw a vertical line, then there is a C, draw a vertical line, then there is a KET. That is what is called a matrix element by us. So how to calculate those matrix elements? And I'll just give you a hint. And with that, I think I have another 4 minutes only, as my clock tells me. And before somebody puts his axe on my throat, I would like to chop my throat myself. So this is the first part, which I will have just enough to tell you only this. In fact, I have not gone through most of the material which I wanted to say, but I think whatever I have said is clear to you. Now, this coupling coefficient, which is known as the 3J coefficient, is also known as the Wigner 3J coefficient, was introduced by Wigner. And as far as you are concerned, as a mathematician, don't bother about the physics which goes on behind it. Some J1, J2, J3 with their projections M1, M2, M3. We read them as columns. J1 with projection M1, J2 with projection M2, J3 with projection M3. And it is written within square brackets. This is known as the Klebs-Gordon or the Wigner 3J coefficient. Now, I got interested when I saw that this coefficient is written as some Kronecker delta function times a phase factor times what is not that del is what is known as the vector addition quantity. J1, J2, and J3 must be vectors, so that J1 plus J2 will be equal to J3. So that vector addition, it is called a triangular inequality and so on. I do not have time to explain that. Then you have a product of certain factorials, product of I equal to 1 to 3, ji plus mi factorial into ji minus mi factorial to the power of half. That's just a numerical factor multiplied by a summation. Now this summation is the one which I would like to emphasize, and with that I will tell you in words what I have done. You see a single sum here over t, right? And it is minus 1 to the power of t multiplied by a whole quantity which is with a minus 1, which means it is all in the denominator, a t factorial in the denominator, a product of t minus alpha k factorial, and a product of beta l minus t factorial. 3 plus 2, 5 terms are there. Now, if you write these factorials, I'm now going to only use words to describe to you what I have done. Write these factorials as gamma functions. All of you know that n factorial is gamma of n plus 1. So write them as gamma functions and make use of the reflection formula that gamma z gamma 1 minus z is equal to pi by sine pi z, or gamma z gamma 1 minus z is pi cosecant pi z. This plays a central role in quantum theory of angular momentum for me. So use that to rewrite this particular gamma functions. See, the factorials are 5 factorials all in the denominator, but 3 of them have got a negative summation sign. So for them, use the reflection formula to get them to the numerator, because gamma z gamma 1 minus z is pi by sine pi z. So 1 minus z, if you now replace z by z plus n, gamma z plus n into gamma 1 minus z minus n is equal to minus 1 to the power of something you will get. If you take the ratio of these two, you will get a beautiful relationship, which will, whenever you get a minus in the summation index, you can use that formula to make it as a plus in the inverse of that. So if you get a minus t in the denominator, when I use that particular reflection formula, it will become a plus t in the numerator. So there will be 3 numerator factorials and 2 denominator factorials, and lo and behold, sir, that is a 3f2 hypergeometric function. And it is the relationship of this hypergeometric function with the symmetries of this coefficient. That's a very interesting topic which fascinated me. You can see, if you write since you are interested in hypergeometric functions, 3f2, which means what? 3 numerator parameters, 2 denominator parameters. So trivially, I can permute the 3 numerator parameters. The value is not going to change. I can because these are numbers. These are complex numbers at best. In a hypergeometric function, all the variables can be complex. Therefore, if it is a 3f2, the first term will be 1 plus abc divided by de, let us say. Now, these values, the fact that you can write this as the next one will be a into a plus 1, b into b plus 1, c into c plus 1 divided by d into d plus 1, e into e plus 1 into z squared by 2 factorial, etc. Now, one of the things which I realized is that I can write this in folded form. Therefore, I got a complete way of computing these angular momentum coefficients very simply by making use of Horner's scheme, and I was able to plot them on the fastest computers and show that they are much faster than what other people have done. It resulted in a series of 4 or 5 papers which I wrote on the connection between angular momentum coefficients and hypergeometric functions, and how hypergeometric functions are used, making use of the Horner scheme for polynomial evaluation. I think it is now 3:30. It will be cruel on my part to extend because it is the last day and you are going to have a valedictory function. I do not want the people who have invited me to give this talk to say that I have exceeded my limits. So I think I will stop now, even though I have said hardly a fraction of what I wanted to share with you. Thank you, sir.
Professor Rao. Thank you, Professor Rao, for interesting talk, which relates quantum mechanics with special functions. If there is any question from audience, please ask or share in chat box.
I have obtained various forms of 3f2 ones which are named after van der Waalen, Wigner, Raka, and Majumdar. And I found that these forms are not independent, they are interrelated, and I got beautiful results out of that. So it's all contained in a monograph which I have written, which is entitled Quantum Theory of Angular Momentum, Selected Topics, that was published by me with my student, V. Rajeshwari, who was a PhD student at that time. It's a Springer-Verlag publication. It appeared in the year 1993. and summarizes the work which I have done. And it is out of this book that I have shown you a few pages when I mentioned these results to you. The 3J coefficient is connected to a 3f2 hypergeometric series and sets of them. That is where I was able to do something which was nobody else had realized. The 3J coefficient is related to a set of 3f2 hypergeometric functions. And in the another coupling coefficient, it is related to either a set of 3-4f3 hypergeometric functions or 4-4f3 hypergeometric functions. And those two, the set 1 of hypergeometric functions and the set 2 of hypergeometric functions, are related to each other through beautiful mapping. Okay, so the lovely results which I have rated some geometry out of that. I do not have the time to mention in this lecture, therefore. Thank you. So two sets of hypergeometric functions were discovered for the angular momentum coefficient 6j, and one set of hypergeometric functions, set of 6, was discovered for the 9j, for the 3j coefficient. And for the 9j coefficient, I even got something better. It is not a single hypergeometric series, thanks to an author writing a note saying the following sentence hit me like a bullet. It said, while the 3j coefficient is a 3f2 hypergeometric function and the 6j coefficient is a 4f3 hypergeometric function, this 9j coefficient is not a 7f6. The moment I read this statement, I said, this is an idiotic statement. Whoever has made it, it is a publication by a person called A.C.T. Wu in a Journal of Mathematical Physics, a very famous journal. But still, when I read that, if you tell me, if I say that I have seen something, it is not this, it is not this, it is not that, it does not define what it is. If you say it is not something, what you are only eliminating one part of it. There are n infinite number of other possibilities which are there. What is it? So the person saying that while the 3j is a 3f2 and the 6j is a 4f3, the 9j is not a 7f6 was the thing which made me worry about that for quite some time, until I came across the simplest form for the 9j coefficient was a triple hypergeometric series. It's a triple series, and the triple series is a triple hypergeometric series. So my quantum theory of angular momentum, the following results were obtained. The angular momentum coefficient 3j coefficient, if it is to be written as in terms of hypergeometric series, you need a set of 6 3f2 hypergeometric functions. If you want to write the 6j coefficient as a hypergeometric function, then you can have either a set of 3 hypergeometric functions or a set of 4 hypergeometric functions. And every one of the 3 elements here in the hypergeometric functions of set 1 is related to the other one in set 2 through reversal of series argument. Beautiful result. But these 3 becomes those 4. That is very complicated. How does a set of 3 become a set of 4? Well, you have to understand the whole of the physics before you will be able to see that. And it fits in like a key which opens the lock.
Thank you, sir. Is there any question from audience?